All right. Good morning, everybody. I don't know if you recognize the music, but it was from Interstellar. I picked it because the astronomy students have been watching Interstellar in their classes, and I've been hearing that soundtrack for like the last week. The aim for today is to get chapter 17 all done. There's stuff on the board that is not for you. Okay, that's for my Physics 2B students. They're taking an exam right after you guys are done. They need this. So, this is Physics 2B stuff, right? I'll look at it. All right, so we left off yesterday talking about standing waves on strings. We learned about this new kind of wave and the mathematical relationships between harmonics and fundamental frequencies and all those things. The thing we want to do today is to do the same thing, but with pipes, which is why I was playing you organ music before. Let me adjust something really quick. So that the microphone is doing its job. There we go. The organ, right, as a musical instrument, uses standing waves in pipes. An organ, well, the organ we were seeing there at the Royal Albert Hall in London, has more than 15,000 individual pipes in it, right, that are attached to that keyboard in various ways. We're basically going to be learning the physics of why trombones, trumpets, French horns, clarinet, saxophone, basically anything that causes air to vibrate, right, to make a noise, is functioning. The standing waves get formed in our tracheas as we try to produce speech. So we're moving in that direction where we're unlocking the basic physics of all of this sound that's around us. You need to understand very critical thing here, right, when it comes to standing waves in pipes. Physicists refer to two kinds of pipes that exist really in the universe, okay? Two very broad categories. We have what's called an open pipe. And by open, we mean that it's open on both ends. And then we refer to a closed pipe. But notice, it's closed only at one end. It's really hard to get sound out of a pipe that's closed on both ends. Unless you're inside the pipe and it's closed on both ends, but that's a different situation. So it turns out a pipe closed on both ends is mathematically exactly the same as a pipe that's open on both ends. But if I say open pipe, what I mean is both ends are open. And when I say closed pipe, I mean it's closed only on one end. The key difference here has to do with the boundary conditions. We talked about boundary conditions yesterday, where for the string, we had to have nodes on either side because the string is tied down. In an open pipe for a standing wave in air, the boundary condition shifts. You have to have antinodes at each end. The air is free to wiggle. There's no obstruction there that would cause the air to stand still, and so it will wiggle a lot there and form an antinode. Now, you can't just have an antinode and an antinode. What do you have to have in between two antinodes? A node, right? So the pattern, the fundamental pattern would be that for an open pipe. In a closed pipe, you have an antinode at the open end, but the closed end is a node. And we're going to come back to this, and we're going to lay out all the mathematics, but I just wanted to make sure that you had a picture, right, the same picture in your mind as I have in mine when it comes to talking about it. And we'll talk about musical instruments that look like this. Most of them look like open on both ends, but there are some that look like they're closed on one end, and we'll get there. Before we get there, though, I mean, how do you... Okay, so what kind of wave is a sound wave? When a wave exists in air, is it transverse or longitudinal wave? Remember? It's longitudinal, right? Air can't wiggle, right? Perpendicular to the direction the wave is traveling. So the waves are coming at you as these compressions. And it can get really hard to try to picture what's going on with a longitudinal wave in the first place. I showed you one on my slinky, right? So you can kind of see that. This is a wave in a pipe, okay? And there's a plunger down here, and the plunger's like doing simple harmonic motion at the end. And so it compresses the air, pushes it forward, and that compression moves. And then another one comes behind it, and you just keep making these compressions to form the wave. This is what our vocal cords are doing all the time. They got two flappy pieces of skin inside of our throats, and they bang together, they open and close, and they either stop the air or let the air out. And it's those series of compressions, right, that travels outwards. But what does so that's just a traveling wave. That's not even a standing wave yet, right? That's just letting the wave go. To make a standing wave, we need reflection to come back, right? We need it to overlap so we get constructive and destructive nodes and antinodes. What the heck does that look like for a longitudinal wave? Like we saw yesterday with the transverse standing wave, the string was vertical, but it was a horizontal, right? When we were drawing them, right, the waves were going back and forth horizontally, but the nodes and the antinodes were going up and down. So that's a transverse standing wave. But what does a standing wave, a longitudinal standing wave look like? It's really hard. And so we're going to make it worse by showing you this video. The way we're going to make it worse is they're going to make a sound. I'm just going to warn you. They're going to make a sound that sounds a lot like fingernails being dragged over a chalkboard. Okay? The reason they're making this sound is because they want to show you the standing wave pattern that exists inside that clear tube that you see the arrow over.
We'll use this long glass tube and some cork dust to demonstrate standing sound waves in a column of air. The standing waves will be produced by driving the air in the tube with the output from this rod.
Here comes.
When the standing wave forms, the motion of the air pushes the cork dust into regularly spaced piles.
What's that right there? Yeah, that's an antinode, isn't it? And then the node right here. See how the dust just doesn't move? Here it was moving a lot, but then there were places where the dust wasn't moving at all. So a standing wave in air and in a pipe is going to have, like, sections of the pipe will have air that's moving back and forth a lot. And that would be our antinode. And then right next to that, there'll be a spot where the air doesn't move at all. And that's our node. And then there'll be a place where the air is moving a lot. And then there'll be a place where it's not. And then there'll be a place, right? Okay? And it's those antinodes aren't going anywhere. They're there inside the pipe doing a lot of wiggling back and forth. And on either side, there'll be places where there isn't any motion. So how do you draw that? Like literally, you take like a pipe and then go, okay? It goes bad. It goes bad really fast. So what we do in physics is we don't even bother, okay? And we just pretend that they're transverse waves. We know that waves in pipes are compressional, longitudinal waves. But in order to help us visualize what's going on, we will go ahead and draw just the standard football shape of standing waves, nodes and antinodes, all that sort of stuff. And just kind of go wink, wink. We know these are longitudinal waves, but it doesn't matter. The physics, the mathematics, everything works out to be the same, whether we draw it like that or we draw it in the real or what's actually happening case. So this is an abstraction, but it's an abstraction that helps because we've already seen, okay, these kinds of standing waves before. But notice our boundary conditions are slightly different. So where on the string we were kind of drawing footballs, right? Okay, we kind of have like half of a football meeting half of a football right there, right? But the mathematical pattern that we learned last time repeats itself. There's the first harmonic, the fundamental of a pipe that is open on both ends. That is the first standing wave pattern that can be developed on that pipe. We are going from a peak to a trough, like if we follow that top line right there. Right, we start here and we come down, right? That's peak to trough. How much of a wavelength is existing in that pipe right now? If we just go from a peak to a trough, is that a whole wave? No, that's only half of a wave, isn't it? Because a full wave would be a peak to a trough to a peak, or a trough to a peak to a trough. Like you gotta get back to where you started, right? Okay. So this is only half of our wave, and so our wavelength will be twice the length of this pipe, but that's exactly the same equation we got when we did standing waves on a string. So that's cool. The second harmonic. Okay, how much of a wave is here? We're going peak to trough to peak. How much of a wave is that? That's 1. And so our wavelength is equal to the length of this pipe. Okay, same exact relationship we had for a string. Third one, looks like we go 1.5. What's happening here? Standing waves on a string, standing waves in a pipe, are they any different? Mathematically, they're not. Technically, the boundary conditions have shifted, right? But the mathematical relationships between these things, right, stays the same. So our nth harmonic will be n times whatever the fundamental frequency happens to be. Our nth, so we can write nv over 2L, where our fundamental is v over 2L. This is exactly the same math that we had last time. Remember, lambda n was 2L over n. Okay, so that's exactly the same toolbox, which is nice, right? You don't have another toolbox to learn or memorize or figure out. It's the same as we had before. The key difference here, though, has to do with these boundary conditions. I keep harping on them. When it came to standing waves on a string, the way that you knew which harmonic you were on was counting the number of antinodes, right? The string had 3 antinodes, we knew that was the third harmonic. Okay, take a look at these pictures. Which thing, the nodes or antinodes, match the harmonic number? This is the third harmonic. How many antinodes are there? 4. But how many nodes are there? 3. Look at the second harmonic. How many nodes are there? 2. First harmonic, how many nodes are there? 1. So when it comes to standing waves in an open pipe, count the number of nodes. The number of nodes will tell you which harmonic you are on. So count nodes, okay, instead of antinodes. And the speed. What is the speed of a longitudinal wave in a pipe that's filled with air? It's 343. It's the speed of sound, right? So we just use 343 meters per second, unless we're told otherwise, right? We use whatever the problem tells us to use, because the speed of sound in air does vary with temperature and pressure and a few other things. But other than that, we got the same mathematics, same style of problem solving that we had before. Our picture's more or less shifted. The waves are shifted to the side just a little bit. Okay, this is where it goes off the rails just slightly, okay? And we got to deal with the closed pipe now. Sorry, my allergies are bad. And I'm like getting a cough just from my allergies. All right. How much of a wave? So here's this closed pipe, right? Open on one end, closed on the other. Antinode here, node here. On a wave, if we go from a peak and not even make it to the trough, right? We're just going from peak to equilibrium. How much of the wave is that? It's 1/4. A full wave would take us from a peak to a trough back to a peak, right? Okay. What we're doing is we're going from this antinode to this node right here, right? That's only 1/4 of my wave, which is why they've said, right, the wavelength here, if this pipe were 1 meter long and I've only got 1/4 of my wave inside of the pipe, that means my wavelength is 4 meters, right? If I had the full thing in there. And when you derive the relationship with frequency, okay, you get V over, this is different, right? V over what? 4, not 2. The fundamental for an open pipe, fundamental for a string, was V divided by 2L. Here, our first harmonic, our fundamental, V over 4L. Okay. Now something even stranger happens. Notice, this says first, and this one does not say second. What happened to the second harmonic? Remember those boundary conditions I told you about? The pattern is always antinode node or node anti. You can never have two antinodes next to each other. You can never have two nodes next to each other. So, for a closed pipe, can I just drop a node right here in the middle? No, that's not physically allowed. That's not how standing waves work. Can I just put an antinode here? What am I forced to do to get this to fit? Antinode, node, antinode, node. You see that? I had to put a node-antinode pair in order to satisfy the boundary conditions for this situation. If I want to do the next one, again, I know I have to start with antinode and I know I have to end with a node. I know that. So now I've got to put in two node-antinode pairs in order to keep the standing wave pattern. The physics of this pipe is telling us that every even harmonic doesn't exist. Remember how yesterday on that string, as I was tuning it, if I didn't get just the right frequency, the pattern kind of fell apart. It was sort of random, it wasn't doing much, okay? Same thing's going on here in this pipe. A pattern must follow node, antinode to be a standing wave. The only time that's going to happen for a pipe that's closed on one end is at an odd harmonic number. The first harmonic has how many nodes in that top picture? 1. How many nodes are there in the third harmonic? 2. How many nodes are there in the fifth harmonic? 3. So with a pipe that's closed at one end, you really just can't count anything. I mean, technically, anyway, it doesn't really work. The pattern falls apart in terms of counting nodes and antinodes. But mostly you just draw a picture and you know you have a node on one side and an antinode on the other and just fit your node-antinode pairs in. So the closed pipe is a little more difficult, okay, conceptually in dealing with it. It also has one big hazard, especially for Mr. Balogh, okay? Because when I write my nth harmonic, it's still n times the fundamental. It's just the fundamental is V over what? It's 4. How often do you think I've made the mistake of just writing 2L and I keep going, right? It's an easy mistake to make. They're both even numbers, right? Maybe you're better at it than I am, but man, I tend to screw that up. And so I've really tried over my career to like set that. Like when I sit down to do a problem with standing waves, am I, thinking about it in terms of like, am I sure this is a closed pipe? Am I sure this is an open pipe? If it is, what equation do I need to use? It's very easy to mix up in my brain. So we still have this relationship. The third harmonic still has an n of 3. It's 3 times the fundamental, whatever, okay? Our fundamental is a little bit different. If we put those two equations together in its more compact form, we've got that, okay? Our lambda, our wavelengths are 4L over n. But n is odd only. There will never be even harmonics in a closed pipe. It just doesn't happen in nature or in the mathematics. So I need to warn you about something, and this is something that I have tried very hard to correct during the course of my career. I'm still working at it, and we're making some progress. In the grand scheme of things, it's not going to change, human life as we know it or anything like that. But students have been horribly confused by acoustical physicists who can't be consistent with their terminology. And so you may have already run into this, but you might have also... You shining a laser at me? No. The term harmonic has been abused in the past and hasn't had consistent meaning. The term resonance has also been kind of squirrely, and there's another term out there to describe these harmonics, which is the term overtone. Now, in my class, I will always refer to a harmonic as being the same value n, right, that you see on there. That's just very consistent, and it's something that keeps students from being confused, right, with what's going on. But be warned, if you go to YouTube or you pull up a website or any of you read a different book or something like that, okay, then there is going to be confusion because some textbooks will refer to this second, what I'm calling the third harmonic, they will refer to that as the second harmonic. And you're like, why would you do that? Sometimes they talk about resonance, the fundamental resonance of a pipe, or the third resonance of a closed pipe. That term resonance, where the tube is behaving according to some kind of, that resonant phenomenon where it's forming the standing wave. The third resonance of a closed pipe could either mean the third harmonic or the fifth harmonic, depending on the person who's using the word. It's horribly confusing. And again, I apologize. I don't feel responsible, but I am a physicist, and other physicists do this, and I yell and I scream at them every time I see it. I just call it out because it's horrible. It's confusing. Not just the physicists, but the students as well. The term overtone. Sometimes physicists will call the first harmonic and the fundamental, but then they'll call the next one the first overtone. It's really like in an open pipe, the second harmonic can be called the first overtone. Third harmonic can be called the second overtone, so on and so forth. But in a closed pipe, the first overtone is the third harmonic. So, again, I tell you this because I know you use a variety of resources. This book is very good about using the term harmonic and sticking with it, right? If you're ever confused on an exam, what are you going to do? You're going to ask me, right? Because this is not a test of whether you can figure out all the different systems that acoustical physicists use to describe what's going on here, right? I'm more interested in, do you know if it's open? Do you know if it's closed? Can you work your way right through the physics of the problem? So if you're ever confused, and this sneaks in a lot. Homework problems at the end of a chapter are not written by the author of the book. They're written by other physicists, and then they're solved by graduate students, okay? And so it can be a mishmash sometimes. And even I slip up all the time. So I'm reading a problem like, oh, that's a good problem to assign. I don't even catch that they use the terms weirdly, right? So again, if you feel like you've understood the problem, but your harmonic number is off, it's probably not you. It's probably how they describe what was going on. And the examples I'm about to do, I've made confusing on purpose, just to kind of show you, right, the kinds of things that you can run up against. And again, I'm an optical physicist, okay? I'm sure we have these problems, but we don't understand. The acoustical physicists, they are all over the place when it comes to their terminology. So let's do a couple of examples of figuring out how to do standing waves and pipes. And then we are going to talk about music. How it's made, why it sounds the way it does, all that kind of stuff. Okay. First thing to do, right, is to contextualize and figure out what kind of problem. Now, obviously, I've taught you about standing waves and pipes, so we know that's what this problem is going to be about. And we are, what kind of pipe do we have here? It says it's open, right? And they've also told us that this open pipe has a fundamental frequency. So what I like to do is I like to draw my pipe. It's an open pipe, okay? And we know that it's fundamental. So fundamental is an N value of what? 1. Fundamental is middle C, 261.6 hertz. Okay, so that's what I'm given, right? Okay. The third, here we go. The third resonance of a closed pipe. Okay, first of all, it's a closed pipe, right? So it's going to look something like this, right? And what do we know about the pattern for a closed pipe? The N values, they can only be what? Odd, right? So we have like N equals 1, N equals 3, N equals 5. So this problem, I pulled this straight out of the textbook. This problem says third resonance. So in my mind, I would go straight to third resonance would be N equals 3. Kind of like the harmonic number kind of thing, right? But as it turns out, and the only way I knew this was to go look at the key, okay? It's the fifth. So, again, I don't want you to worry, right, in this class about this issue. But I'm just warning you, as you see other sources out there, it can be confusing. If I put this term on the exam, if I say it's a resonance, right? You can't shoot me or anything, but you just throw your hand in the air and say, Mr. Balogh, what do you mean? Right? And I will just tell you, okay, that's the fifth harmonic or whatever, right? So as you're doing your homework and all that kind of stuff, just be aware, right? Sometimes these words can sneak in, and again, even I have lost the ability to kind of understand that it's a problem. Okay, so it turns out that the third resonance is that one, okay? It's N equals 5. I would rewrite this problem if I was putting it on an exam. I would rewrite this as the fifth harmonic of a closed organ pipe. And when I use that word harmonic, what do I mean? N equals 5, right? If a problem were to say the second resonance of a closed pipe, well, now you know something's very wrong. That can't be the harmonic number because there's no even ones. So the second one must be the third. Anyway, and like I said, I apologize. It's not my fault. Not my fault. Okay, so we know that the fifth harmonic of this closed pipe has the same frequency as the fundamental of the open pipe, okay? And they want us to find the lengths of both of these pipes. Is there a tool in the toolbox that relates frequency and length? What have we got? We've got NV over 2L, but where does the NV over 2L go? It goes with the open pipe, doesn't it? Because what does the closed pipe say? NV over 4L. Again, that's a mistake I make all the time. Okay, well we know this is the fundamental. Do we know what V is? What's V? It's 343. This is a standing wave in air. Speed of sound in air. Okay, they don't tell me what that is, so I'm just going to assume it's 343. So that means I can solve for this length. It's going to be V over twice my frequency, so 343 over 2 times 261.6, giving me a length of the open pipe of 0.656 meters. And then over here I pull off the same thing, only it's F5 equals 5V over 4L. Solving for L, that is going to be 5V over 4 and then the fifth frequency. So it's going to be 5 times 343 all over 4 times 261.6, which gives me a length of 1.64. So is the math hard? Not really, right? Multiply, divide, basic algebra. But making sure that we have conceptualized properly, that we have the right picture in our head to be able to apply the tools correctly, is where you need to be focusing all of your efforts, okay? Don't be satisfied with just letting the Go tutorial give you the equation or something, right? Understand why that equation is the one that applies, and you'll be much better off. Let's do another one. Okay. I want you to work with each other. Just want you to turn to each other, okay? And talk about what you are doing to try to solve this problem. Right? Talk about whether we've got open or closed pipes. Talk about the equations you think might help you find the fundamental frequency of the original uncut pipe. Do the problem together. Draw the pictures together. I'm going to give you like, I don't know, 3 to 5 minutes. I'm going to wander through the room, right? If you're stuck, you need to let me know so I can help unstuck you and get started. So turn to each other and get started and get going. Start with a picture. Draw a pipe and cut it. Notice you are not cutting this in half. You don't know where this pipe gets cut. As soon as you get some kind of picture down, turn the person next to you and start showing them. Does your silence mean you're stuck, or does your silence mean it's too early in the morning? Or all of the above? Do you need help? Need help? So there's my metal pipe, okay? They don't tell me like if it's closed at one end or not, so I'll just go ahead and assume that it's not, right? And then I come along and I cut it into two pieces. I'm just picking a spot. They don't tell me it's in half or anything, right? In fact, I know that it's different lengths because one of those frequencies is 256 and the other one is 440. So one of those two things, right? And so the different frequencies correspond to different lengths, right? Whoops. Because frequency and length are related to each other. The longer, the bigger L gets, what happens to the frequency? So go up or down. They're inversely related to each other, so it goes down, right? So which of these two pieces of the pipe, the longer or the shorter one, has the lower frequency? The longer one. Like you just told me that the length, as the length gets bigger, the frequency goes down, right? So this longer one must be the 256, and this one has to be the 440 hertz pipe. All right. So we know that, okay? And we know that those are the fundamental frequencies for both of these pipes. So if we want to find the original uncut length, we need to find the lengths of each of the individual pieces. And when we've got that, we can add them together. So how do we find the length if we know the frequency? It's right there, right? If it's the fundamental frequency, that's V over 2L. So the length is going to be V over twice the fundamental. Again, we'll use 343 over 2 times 440 to get me a length. And over here, again, open pipe. So I can use exactly the same equation, 343 over 2 times 256. And I did that. I got 0.67 for the 256, 0.67 meters. And for this one, I got 0.39 meters. Okay, so if those are the lengths of the individual pieces, then I can just add those two numbers together. And I get the total length started off as 1.06 meters. What else they asked me? How long? Oh, I did that one already. I did part B first, right? So now that I know the original length, what was its fundamental frequency? It's right there, right? Its fundamental frequency was 343 all over 2 times whatever the original length was, 1.06, and I got 162 hertz. So in summary, open and closed pipes. The open pipe has the same mathematical relationship as standing waves on a string. Same toolbox. Instead of counting antinodes, we count nodes. But when it comes to closed pipes, we do have to be careful because the toolbox changes slightly. There's a 4L instead of a 2L. And there's only odd harmonics. And you can't count anything. You can't count nodes or antinodes. And sometimes just having a picture is better. Before I can tell you exactly how all the parts of the orchestra work, I do need to show you standing waves in 2 dimensions. Every standing wave we've done so far has been a 1-dimensional standing wave, which sounds kind of funny because the wave, right, we've got a horizontal string, but it's wiggling perpendicular to that. It seems like that's 2 dimensions. It's actually 1-dimensional standing wave because it exists on a 1-dimensional structure. A string just has length. A pipe just has length. 2-dimensional standing waves are generated on structures that have surfaces. And as far as the orchestra is concerned, that means the percussion section, okay? Or as we used to call it, the treble section, because the percussionists were always in trouble, along with the trombonists. I'm gonna play a video, it's gonna have flashing lights in it.
Have you ever wondered how the head of a drum vibrates when it is struck? We'll use this flexible rubber diaphragm and this speaker to show some of the forms of vibration. The speaker drives the rubber drum head with sound waves from beneath.
Comes flashing light.
Here is the fundamental vibration of the drum head seen with a strobe light to slow down the motion.
You see how the whole surface is kind of doing one big antinode?
Here is an oscillation at a higher frequency. Notice the circular nodal line.
So the node is no longer a point, it's a line.
Here is a different type of oscillation with a nodal line running across the diameter.
Okay? So it's a lot more complicated, isn't it? You go into that 2 dimensions, you don't have nodal points or antinodal places. We have nodal lines and antinodal surfaces that are doing things.
The frequency is set as
This is
shown
a
by the
flat
inside
plate
of
that
the
they're
lower half of the
vibrating.
picture,
Thankfully, we
and
can't hear it.
poured onto the plate.
And then they pour
The
sand onto the
illustrates
plate.
the standing wave pattern by gathering along the nodal lines.
Those are nodes.
Now the frequency is adjusted to show various standing waves in the plate.
Change the frequency, you change the standing wave pattern on the surface of that plate. And the sand will go to wherever the plate is not moving, right? It gathers at those nodal points. And they're going to show us a bunch of different frequencies, bunch of different patterns, right? Very complex, very cool. I always use that joke, like, who needs drugs? Yeah, physics.
The wooden plates on a violin would exhibit this type of oscillation.
Does the shape of an instrument matter? Okay, right? So this is where, now that we know what we know about standing waves, we can start talking about how music works and how it's produced, and so on and so forth. So I'm going to limit this discussion to the classical orchestra. For those of you that, oh, it's so old-fashioned and boring, and blah, blah, blah. Okay. Physics 2B is where you get to talk about rock and roll. Okay, because we can't do electric guitars and modern music without electricity. We got to understand electricity first, right? So this is all acoustical, right, forms of music. So how number one, okay, what does standing waves have to do with any of this? Number two, how do you get a wave that in its very name just stands there? Just wiggles back and forth and never goes anywhere. How do you get that thing to make sound that travels out into the concert hall or whoever's listening to it, right? Okay, so number one, we gotta produce it. Number two, we have to figure out how to transmit it, right? And how does that come back to the shape of an instrument and all of those things. So this is kind of a big topic here, right? But let's start with what is music and what is noise? I know your parents have a different idea, right, as to what noise versus music is than you do, okay? Every generation has gone through this in the last 100 years. But in physics, we have a very definite definition for the difference between music and noise. The thing about musical sound is that it is cross-cultural. Now, I know that different cultures have different, musical scales, and what one might consider music, another might go, but independent of culture, the human brain reacts differently to musical sound than it does to noise. The difference has to do with repetition. Musical sounds, you ask anybody from any culture, you play them a musical instrument or a musical sound, and they will listen to it and they go, I don't recognize it, I don't like it, but I can tell that that's music. The way you know, look at the waveform, right? That's being generated by a musical sound. It repeats itself. It's cyclical. It's even. Noise is random fluctuations in frequency. If you have a white noise app on your phone, if you ask a digital assistant to play you some white noise or brown noise or pink noise or whatever, that's true noise. There are random variations in the frequency, and it sounds like static. It sounds like, can you hear the air handler pushing air into this room? That low hum? Can you hear the projector's fan? That's noise. That's not music. Because those kinds of sound patterns have random frequency jumps in them. And there's no consistency to it. So, when anybody tells you that you're listening to noise, you go, no, I'm listening to a regular repeating pattern in the frequency spectrum. Otherwise known as music. Okay? Beyond that, then we show cultural preference for which notes and which order they're done in and what musical instruments they happen on and all that kind of stuff. Okay. Let's play a game called Name That Tune. Let's see here. I can't see anything on the screen, so I'm going to play. Okay. Let's see. I'm gonna bet that you are going to recognize what I'm about to play for you. So what I would like you to do is try to figure out where you've heard this music before. I do have to I gotta scrub through it here to find the part that you will go, okay. Here it comes. Okay. It's gonna happen here as soon. Here it comes. Where have you heard this before? Anybody know what this is? What piece of music? It's one of the most beautiful melodies ever written in classical music. Okay. Where do you think you've heard it before?
I felt like a couple notes here and there were almost reminiscent of like some kind of Disney theme.
Okay.
But then it just
And then it went somewhere
and
else.
then it goes somewhere else.
Right, okay. Like, probably movies? Did it sound a little bit like a movie soundtrack? What emotion, other than boredom, were you feeling as you listened to that? Kind of, maybe awe? Was it like a little bit, maybe not exciting, but just sort of like, the heroes are walking into the room, right? Like, you know,
I was thinking like just a sprinkle of like romanticism.
okay, right? That's getting into the weeds a bit with, right, the age that it's from, okay? In 1906, Gustav Holst wrote a series of musical pieces, 8 of them, each one representing a different planet in the solar system. The theme you just heard was the theme from Jupiter, okay? Now, Holst wrote the music to reflect the Roman god that is represented by the planets. And Jupiter in the Roman pantheon was the king of the gods, right? The head honcho. Zeus, Jupiter, same guy, different cultures, okay? And so, being the king of the gods, Holst wrote a melody and a theme that evoked sort of that grandeur, right? As Zeus walked into the room, right? This big god and telling everybody what to do, right? So it had that hero sound to it. And so, when movie composers like John Williams went and reached for sound for the heroes, it's no surprise that they would borrow from this kind of theming, the trumpets, the French horns, the orchestration that's all there, okay, to evoke that kind of feeling. Like I said, there were 8 pieces in the planets. Of course, I have to play the planets in a physics class, right? Okay. And this is me giving the music department something to do. I'm trying to teach across the curriculum, all right? Okay. So here's another piece that Holst wrote for the planets. See if you can't guess which planet this is, like which Roman god. Close.
Is it Mars?
Yeah, this is Mars.
I was gonna say Aries, but I knew that was like.
So Hades and Ares were the gods of, well, Ares is god of war, Hades is the god of the underworld. We don't have a planet called Hades, but we do have a planet called Mars. So, what's the emotion of this music? This is the music that plays when you're walking into the exam, right? Okay, the dread, the sensitivity, right? Okay. Here comes a part of the theme I think you're gonna recognize. Wait for it. It's coming. What is that? Right? When John Williams wanted to write a theme for the worst bad guy ever for this 8-year-old, he reached for Mars. That theme that you are hearing, that is directly pulled out of Mars, the god of war, right? It was a total like music nerd Easter egg, right? But of course I didn't learn until I was older, any of that kind of stuff, right? But just music has that ability to evoke emotion, right? And it's no surprise that composers will reach for orchestrations, the kinds of instruments, the sounds that they are making, how they're making the sounds. Like, there's just so much going on here. And the reason I'm doing this is because I want you to cue in on something. Here's a very famous piece of music. Okay? This is Beethoven's Moonlight Sonata. Okay? It's moonlight, right? You're supposed to go to sweet. I think this is a beautifully haunting piece of music. I don't like it. Mostly because I had to play it over and over and over again for piano lessons, right? Okay? So it's kind of been overused for me. What instrument is that? That's a piano. And how do you know it's a piano? Sounds like a piano, right? It's got that distinctive piano sound. Okay. Those are violins. Ignore those for a second. What's that? That's a flute. Okay. How do you know it's a flute? Sounds like a flute. Right? Okay. Or piccolo or some. It's got a very different sound to it, right? Okay. Here's a rather famous piece of music. So that's a piano. Anybody know what musical instrument that is? It's a cello. Okay? It's called the Swan. Very famous by Yo-Yo Ma, another great cellist of our age. You can tell the difference between the cello and the piano. Even though they're playing notes in the same scale and some of the same notes over and over again, you can tell the difference between those sounds. In music, this is referred to as the timbre. Cannot stand how some words are spelled. Okay? The timbre of a musical instrument. It's a musical instrument's voice. A piano and a flute and a clarinet and all the instruments in the orchestra can play the same exact note. And you can tell the difference between each of those musical instruments. That's timbre. Why does this, like how? How is it? I mean, obviously you sit down, you learn what a piano sounds like, you associate the word with that. But what is it physically that is going on that allows us to distinguish the musical voices of instruments and see what the different instruments are doing and all that kind of stuff? That all comes back to standing waves. When a musical instrument generates its sound, there is a complicated and complex coming together of the standing waves that are forming in the instrument, how the instrument itself is vibrating, how it's interacting with the air around it, and how that sound gets pushed into the room. The standing wave patterns that I've been showing you, like those first, second, third harmonics, so on and so forth, all of those things are happening at the same time. When a musical instrument plays a sound, it's actually producing first, second, third, fourth, all the way up to like 10th, 20th harmonics, depending on the musical instrument. And they're all happening on the string at the same time. And so rather than just sine wiggles, you will get complicated waveforms that are still repeating each other. On the screen, tuning forks produce their fundamentals only. Okay? A tuning fork just plays a singular note. And so it will just be a sine function. But other musical instruments will have other harmonics in their waveforms, and you can get a fingerprint for what the different musical instruments' waveforms look like. You can take those fingerprints and mathematically strip apart the different harmonics that are being formed and see how strong those harmonics are relative to each other, and you get these things that are called frequency spectra. The takeaway here that I want you to realize and appreciate, tuning fork has just got that fundamental, but every other instrument, here just flute and clarinet by comparison, has a different fingerprint of harmonics that are involved in producing its noise. Do you see here how, like in the flute, it's actually the second harmonic that seems to be dominant? Okay? Our brains clue in on the first, that lowest frequency. Our brain goes, oh, that's the note. But then other harmonics get overlaid on top of that, and that's what helps our brain go, oh, flute, or oh, clarinet, or oh, piano. You see how the clarinet has got some higher harmonics in it compared to the flutes are often referred to as like a pure sound, right? And clarinets are more of like a moody or a muddy, right? It's just, they have more overdub. The reason a piano sounds so like rich and full is because pianos will sound harmonics up into the 20s and 30s, right? Harmonics. It just has this fuller sound to it. I'm not saying one's better than the other or not, right? That's down to personal preference. But there are distinctions in the waveforms for every musical instrument, and that's what gives every musical instrument its timbre. One.
Why does the flute have like 1, 2, and 3 harmonics and not the 1, 3, and 5?
Good question. That's because flutes, clarinets, trombones, every woodwind in the orchestra is an open pipe. And you're like, wait a second, Mr. Bailey. No, it's not, right? I mean, obviously one end is open, right? On the trumpet, right? The open end, right? Blasting into the waking the dead, whatever the trumpet's doing, okay? And the other end of the trumpet seems closed, isn't it? The part where the trumpeter has pushed their lips into the mouthpiece. That's not a node, okay? That's an antinode. Why is it an antinode? Yeah, what's the trumpet player doing? Into the end of the trumpet, okay? They're buzzing their lips into that mouthpiece. What's the clarinet player doing? Well, probably killing geese. That's what I did a lot when I was playing clarinet. Because if you blow onto the reed incorrectly, you don't get your embouchure right, it sounds like a goose has died. Right? Okay? But by getting that reed to flap up against the mouthpiece correctly, that's an antinode. There's a lot of displacement and pressure changes that are going on there. So all musical instruments, all the woodwinds are open pipes until they're not. Any trumpet players out there? Willing to admit it?
I mean, I played it a bit in elementary school.
Okay, right. Did you ever have a mute for your trumpet?
I did not.
Oh, so your family really hated you when you were practicing.
It just wasn't covered.
Okay. One way to change the volume and sound of a trumpet is to stick a mute into the end. Okay? Now, from the name mute, we obviously know the volume goes down, right? But it does something more.
Let's talk a little about trumpet mutes. A mute is an appliance that you put in the bell that changes the sound of the instrument. Open or without a mute, the trumpet sounds like this.
Very bright.
Sometimes composers will write for a different color for the instrument, and you get these by taking a mute, just like this, and putting it inside the bell of your horn, twisting it slightly so that it stays and doesn't fall out. That's very embarrassing. And this will change the color of the sound. This happens to be a harmon mute, and this one sounds like this.
You see how it changed the sound of the trumpet? Didn't sound as bright anymore? That's a closed pipe. Where's the antinode? At the mouthpiece, okay, where the is going in the end of the trumpet, right? Okay, but the node is where the mute is. The mute has stopped air from flowing. You're like, well, how do I hear anything, Mr. Balogh? More on that in a second, okay? But now we've introduced a closed end, which means that all the even harmonics get stripped out, and all we're left with is odd harmonics. This causes this instrument to sound muddier. In jazz, they'll use a mute to pull off a more mellow jazz trumpet sound. Some musicians refer to it as a sexier sound, and so you start worrying about them a little bit. But it's a way to change how the instrument sounds. Coming back to the organ, In medieval Europe, if you were friends with the king or the knight or whatever, and you were in favor, you probably got to have a cathedral built in your town, and that cathedral would have a pipe organ in it, and that pipe organ would have thousands of pipes and lots of sound and all that kind of stuff. If you were not in favor with the king and you were like, helping all the serfs through their horrible existence, you might have a smaller church, and inside it you might have what's called a pauper's organ. That's an old-timey word. Does anybody know what a pauper might be? A what? Not a fake. It's a poor person. There's another word for a poor person. A pauper is a poor person. So a pauper's organ would be made, instead of out of metal pipes, they'd all be wood pipes, and the material does change the sound a little bit. But more importantly, they would make the entire organ out of closed pipes. So closed pipes are cheaper to make than open pipes. For the same material, you would need half the length. Remember the V over 2L versus the V over 4L? In a pauper's organ, they could get away with half the length. So if you wanted to do middle C, you only needed a pipe that was like this long instead of this long. And that saved material in producing the organ. I don't think there's any pauper's organs in existence anymore because they were mostly made out of wood and the wood would rot away, but the cathedrals and the main towns and the organs were all kept up over the centuries. But they've been reconstructed to see what they sound like, and they do. They sound like a very muddy, like an organ that's being played underwater, almost. It's just because they're made exclusively out of closed pipes, and all of the even harmonics are gone. And so it just sounds different. So how do we hear a musical instrument in the first place? Because it's got standing waves that are going on inside of it. Well, the body of the instrument, in the case of a trumpet, the shape of the bell at the end. For a violin, the actual shape of that instrument has been evolved over the centuries into the shapes that we see now. Not by physicists or mathematicians saying this would be the way it is, but by artists and craftspeople who worked to coax a sound out of the wood and catgut and strings and whatever it is they were throwing together to make the beautiful music that we get to enjoy today. It was an evolution of finding a shape that would take the vibrations on those strings and amplify them, produce standing waves in the body of the instrument that would then couple to the air molecules around it and send that out into the audience. The shape of our theaters is an evolution over thousands of years of trying to solve this problem of how do we get one sound to the most people. I mean, look at this room, right? You guys, I don't have a number of students sitting behind me, right? We don't do lecture in the round, right? Come out here, right, and talk to you, because the people behind me they hear worse, right? And so all of this has been tuned for getting sound to the most people, right, in a way that produces good sound. The Stradivarius violin, some of the most famous violins in the world, made by Stradivarius in Italy back in the 1600s, can no longer be made again. Science has tried. Artists have tried. They've duplicated in as much as it's possible the techniques that Stradivarius used, the glues that he used. It turns out you can't make a Stradivarius violin anymore because the world has changed. Stradivarius used trees, the wood for his instruments, from a forest whose trees had undergone what's called the Little Ice Age. And the density of the tree wood was changed because of this small ice. There was a couple of years where there was no summer, it snowed in June and July and all this kind of stuff. When Stradivarius went to go harvest the wood, he was harvesting wood from that time period. He lived a little bit after it. Those trees are gone. The climate has changed. The density of the wood is different. And so we can't get exactly the same kind of tone out of a modern instrument. We can get close, we get really close, but it's not a Stradivarius. Music is very much a function of the present. I know that we can listen to music that is hundreds to thousands of years old, right? But really, what we're experiencing happens in the now. And I hope that some of the stuff that I've taught you in the last couple of days will help you have a greater appreciation for all that noise that you get to hear out in the wild. I'll see you on Tuesday. For what? Review. Hope to see you tomorrow in Grass. But if I don't, have a fantastic weekend. It's gonna be chilly. It's gonna be rainy.